Hey guys, welcome to my second video of the change of variables for random variables series. Okay, so today we're going to be going through an example of how to apply this theorem here, the theorem of change of variables. So if you guys didn't watch the previous video, so part 1, go back and check that out. That's really useful in understanding what we're going to be doing in this video here. Okay, so let's go on to the question. So the question is, let x have exponential density of fx, x is equal to exponential to the power of negative x. Okay. And now what we want to do is we want to ask ourselves, so what is the CDF slash PDF of y? Yeah, so y is a function of x. So you can see it's a square root of x. So here I've already drawn a diagram. So I just want you guys to imagine that this part here doesn't really exist, because that's what we're looking for here. So this is the density function right here. So that's exponential. So it's upside down, but basically it's upside down, but it's a diagram so that you guys can understand it a lot better. There. So that's an exponential density there, and then here we have the density of y, but we don't really know that, so we're going to try and find that out. And we're also given how y is related to x. So that's through this function here. Okay, so first off is we want to note the range. So step 1 here is we want to note the range of x. Yeah, so x is greater than 0, right? So that would imply that y is also greater than 0. Okay, so to see how you guys understand this, we're putting in strictly positive values into this square root function, here. So strictly positive values, so that means that this function here would have a positive range, basically. So positive range. So in other words, y is greater than 0. We can also say y is between 0 and infinity, right? So that's part 1, right? And then now step 2 now is identifying whether this function is strictly increasing or decreasing, right? And this function is definitely strictly increasing, for sure. Definitely strictly increasing, because it doesn't really have it doesn't have a turning point per se. So it's always, well, that's not a good example actually. So it's just always constantly going up, and it doesn't really have a gradient of 0 at anywhere. So that's good. So that's good. Okay, so now step 3. So step 3 is now, okay, so now we need to find out what this derivative value is. So what this derivative value is. So we've already got the density of fx there. Now we just need to find the derivative value. So I know it's upside down. So what we're going to do is we're just going to calculate the derivative function first, and then we'll flip it upside down later. Yeah, so super easy with exponential here. So we know that y, oh sorry, not exponential. So we know that y is a function as such, and then we just need to take the derivative of that. So it would be half times by x to the power of negative half, right? This is just like high school calculus basically. And then what we do is we make it look a lot nicer, like so here, and then we have that. So that's pretty good. All right, and now what we're going to do is we're going to say, okay, so that's not entirely what we want yet. So we're going to take the modulus of that. Super easy. So that would imply this, the modulus of dx dy as such here. This value is always positive anyway, so we're pretty sweet. So that would just equal itself again. So it's important we need the modulus, because that's what the theorem says. That's what the theorem requires, right? And then what we're going to do is, okay, so now we're also interested in finding out what we really want, which is that. So I'm just going to plug all of this in, and then let's see what happens. So we've got the first part here, so that's fx here. So this is f of fx here, multiplied by the upside down modulus of that. So it's going to be, how do I write this? So it's going to be multiplied by the upside down modulus, which is, so we can flip it upside down. Let's do that. It's going to be dx, it's going to be dy is equal to this one here. So I just literally took this guy and flipped him upside down like such. And then so now according to the theorem, so this part needs to go here now. So it's now that. Alright. Okay, so now, alright, so notice that our almost final product is this. It's 2ex minus x multiplied by square root x. And then what we do is just, okay, so this is not entirely what we want, because we want the function itself to be in terms of y, not in terms of x. So what we do is we find methods of substitution, right? So how is y related to x? Well, y related to x is precisely through this way, right there. So now all we need to do is just replace anywhere where we could. So to begin, you guys will get it here. So that x, that is just minus x, right? So if we square this, this would imply that it's y squared is equal to x. So that's pretty good. So we'll have y squared in place of x. And then we have square root x, which is just y, right? And so now our final product here, the density of y here is now as such. And now as follows. Actually, I'll write that a little bit nicer. So we want that there, and we want this one here, and there we go. Voila. So that's the answer. So the density of y is simply this: 2 times y times e to the power of negative y squared. Okay, pretty nice. Okay, so that's pretty good. Okay, so you guys are probably asking me, you guys are probably wondering, okay, so how is it that we, okay, sure, we found the CDF, that's cool. I mean, sure, we found the PDF, but what about the CDF? Okay, so the CDF is as follows. So the CDF is pretty easy. All you guys need to do is just take the integral of the density itself. So I'm just going to write the density here first, and then I'm going to write, okay, so I always like to write it. So let's cancel that out. I like to write it like this, so density of y, and just have a t there, and then y here, not the density, the cumulative function. And then we have this one, so minus infinity, then we have t here, and then we have 2y e to the power of y there, and then we have this one. Okay, so how can we make this integral look a tiny bit nicer? So we notice that the range of y itself is actually from 0 to infinity, so we can fix this integrand. So let's make that a little bit more precise. Let's have it as y here, and then we have 0 here. This is precisely the range. And this is where t is. Remember that it only goes up to t, right? It doesn't go up, goes up to infinity. So, but we should put a bound on t. So this is what t would like to be, because that's where the function makes sense. Yeah. And then what we do, okay, so now for the integral part, here's what we're going to do. Is we're going to look for a way to apply a change of variables, right? So my suggested change of variables is actually this. It's going to be y is equal to square root u, okay? And so now that's what would imply that y squared is equal to u here. I'm just going to rewrite that. It's going to rewrite u here, and then what I'm going to do is I'm going to actually look, I'm just going to substitute it in. It's going to be this here, it's going to be that one there, so I'm just going to put e at the front, yeah? It's going to be minus, so square that's going to be u here, and I'm going to put the other part at the back, so it's going to be 2 times y, which is square root u, and I'm just going to write it like so. Yeah, so notice that I've just like kind of move things around a bit, but that will not make a difference. These are just multiplicative. Okay, so now the next step is that, okay, so how am I going to change this such that this dy here, such that it disappears? So first off, what we're going to do is we're going to look at the derivative function. So dy and du, and we've already done that in the earlier parts here. So it's going to be 2 square root u here. And so just to move back to where we were, so just that part there, just this part here, that's the part that we found the derivative for. And then the next step is that we're going to just rearrange this and see what we get. So we're going to rearrange it such that we get, you know, du's and dy's on different sides. It's going to be this, so it's going to be square root u, and it's going to be du, and it's going to be 1 times du, like so. Yeah. Well, actually, wait, no, it's meant to be y, my bad. And then what we're going to do is we're going to now see if we've made a difference in sub form. Okay, and yes, we have. See, the good thing about this is that we have these parts matching, right? And so if these parts match, that means we can just have du in place of that. But the thing that we should be concerned with is also that once we change out this dy here, we're going to have to start worrying about the bounds, because the bounds are in terms of y, right? So this is like y is equal to 0, and this part here is like y is equal to t. So let's do that then. So y is equal to 0 in terms of u would imply that 0 would imply 0 squared. So u is equal to 0. And then t would imply that u is equal to t squared. So now we're going to write this part in full. It's going to be the integrand sign thing, and then it's going to be u is equal to 0. I like to write these equal signs here just to make it clear as to like what bounds we're working with. And this is t squared, yeah. And then what I'm going to do is I know this part is already equal to du, so that's pretty sweet. And then this part will just stay the same, so it's going to be e to the power of minus u du. Beautiful. And everyone knows how to do this integrand. So I'll just do this quickly. It's just going to be this one here. This one's going to be, again, with the equal sign thing. And then we move on to the next line. So that would imply that now that's equal to, actually wait, no, I'm not going to write imply. I'm just going to write equal. Hee. It's going to be that. It's going to be this guy minus t squared, right? Okay. So now, to finish it off, we found that the cumulative distribution function is as follows. It's going to be that. And where t is greater than 0, right? And so like sometimes like, you know, your professors might prefer you write it like this instead. It doesn't matter, because because they're just solid values pretty much, so it doesn't matter. They're just dummy variables in a sense, and that, yeah, obviously as such. So to summarize, what we've got here is that we've got for a random variable of, actually I'll just move that page. So for a random variable of this, of y square root x, where x is basically a exponential distribution of, let's say, degree 1, or in other words, x has a density function. X has a density function of e to the power of minus x greater than 0. Then the density of y would be this. So it would be that there, and then be e to the power of, what was it again? E to the power of y squared here. And then sometimes we should, professors might like you to write it like this. So it's like that, and we'll just write the bounds here. And then that's otherwise. Oh boy, my handwriting. And then the cumulative distribution is as follows. That one part there. And that's all there is, right? Okay, so now let's go back and look at our diagram and see what just happened. So basically what we've done here is we've taken an exponential density here, and then what happened to it was that our random variable was transformed into y, so it was a square root instead. And then what happens is that the new random variable y is distributed as follows, like this way, and that's it. So that's how they're related. So you have this density, and it's transformed by this weird transformation of, you know, square root x, and then you get this new density, which is, I'll just write this out so it's clear for everyone, which is basically like this. Oopsie daisies. It's 2y, and then e to the power of y squared. That's the density right there. And okay, and probably just to make this one clear, the density for this one is just simply e to the power of minus x. Perfect. Okay, thank you guys. Thanks for your time.